welcome. And like Dennis was supposed to present it, but unfortunately, or fortunately, he's getting a baby. So I consider that a good excuse to not come to EC3. So I'm talking to you a little bit like about how you can actually like, or how does ChatGPT actually knows building physics and why this is important. For that, I'm picking a little bit like on my previous speaker because he was talking about like how can we use basically like generalized in AIs for different tasks and buildings, and why new symbolic approaches might be like one part of the solution, right? So I would not agree on the we need generalized AIs. More that we need more specific ones, and I'm going to basically explain why that is important in the next few minutes, right? So one of the few important things here is like when we just apply machine learning models, for example, like to a building prediction or performance prediction problem, right? So then we will quickly learn that works. Yes, of course, I can dump my data in AutoML. Yes, of course, I get a nice model out of it, right? So, and yes, a simple random forest model will do a very perfect job, right? Simply because random forest models always nicely overfit. And the problem with building performance prediction is that we have tons of spurious correlation in the data. Simply said, when you want to predict the temperature in this room, right? So the model will simply learn, takes the room, or take the temperature from the next rooms and the connected rooms, and that will be the prediction, right? So, meaning when I stuff this room with full of people, turn off the HVAC system, the prediction model will still tell you, whoa, well, it's still nicely, basically like will be like nicely 22 degrees, temperature will not change, even of course the situation changed drastically. And that's what you see here. So this is like a simulated experiment, right? So we put lots of people into a room, turned off the HVAC system, humidity is increasing drastically. Machine learning model, the orange one, simply says nothing is happening, everything is fine, humidity is not changing at all. Right, so because machine learning model did not learn the physical relationships that actually determine the behavior, it only learned correlation. And that's the problem with basically like all these machine learning approaches, right? So that's why traditionally we would do simulation for those cases, but the problem with simulation is we need tons of parameters that we really don't know, particularly for all the existing buildings, right? So now the question is, does neural symbolic models actually work better? And one of the typical approaches there is you take graph neural networks, right? Why? Simply said, because in a graph neural network, you have a graph layer and neural network layer. In the graph layer, you actually can constrain the neural network layer in which connection actually should learn. Right, so and this allows you to kind of like tell the neural network layer, okay, only learn these physical relationships and ignore the other stuff. Right, so and that results in models that are way much, or like a little bit like physically constraints, not completely, but better physically constraints than normal neural networks, right? So, and that is in theory, we will see, improving the prediction performance, right? So the only question is, to create that basically like adjacency matrix which you need for the graph, you actually need to manually model that because this needs to be building specific. And that's why basically where I say like we don't need more generic models. These models need to be building specific because each building, each basically like building layout, all the physics in each buildings are different, right? So, and that's why you need to adapt this basically this adjacency matrix or the graph underneath, right? And how do you do that? So the simple approach is you just basically like take a BIM model, extract basically like the building structure like this bot. You take a brick for the sensor data, and what you get is a small little graph that shows you, yes, I have a room with 4 sensors attached to it, and like a HVAC system supplying the room, and part of the sensors are also attached to the HVAC system. So the problem with this little graph is that we don't know the causality because we did not put that into Brick, right? So when we created Brick, we wanted to have an ontology that allows us to simply label the sensors and overcome this interoperability problem that my previous speaker also was talking about, right? So, and that was the main purpose of Brick, right? So the only problem is that Brick does not contain the physics, and that's what we actually need to put into the model. Now the question is, where do we take that from, right? So one way to do that is actually by reasoning. And for reasoning, you need rules. Now the question is, why not simply ask ChatGPT, ChatGPT knows everything, right? So why shouldn't we then really ask ChatGPT for these building physics rules, right? So because that should be general knowledge which should be contained in ChatGPT. So we did that, right? So, and what you actually need to extract is a little bit more complicated. So you not just simply say like, okay, connect me those sensors. You actually need to understand a little bit like, you actually need to model the physical properties in the rooms, right? So because they're also are unobservable properties that you do not sense, right? So you need to consider that when you actually want to understand the physics, right? So that's basically like why we extract these unobserved properties or partially observed properties, right? So and then we extract the property relationships, and then we can, with reasoning, create a fully and connected graph. That's it, right? So now you have the graph that you want to put into the neural network, and the important thing is that this graph is now building specific. So when we have a different building layout, when we have different building physics, because, for example, we don't have cooling, we only have a heating system, or the opposite, right? So then you get always out a graph that is specific for that situation. And that's what you want, right? So because then you can learn not just correlation, but actually the causality in the system. We did an evaluation of that, right? So simple simulated environment, we used IDIs for building physics simulation because we wanted to be able to create failure cases, because that is normally where these typical performance models or machine learning models fail, right? So that's why we need to have an environment where we actually can create failures. Has about 33 sensors, 2 connected rooms with a corridor, simple setup, HVAC system feeding these rooms. And then you get something out like that, right? So when you follow the process, you get out a graph that looks like this, and this is the causality graph of these 2 rooms, right? So you have like the 2 rooms on the left side actually, right? So and the rest is on the right side, you primarily have the system behavior, right? So, but you want to get something out like that. We also have a ground truth graph. It looks a little bit more complicated than that, is missing some of the temperature behavior here, right? So, and we achieved that with the GPT 1.0, right? So with ChatGPT, and we simply asked or provided ChatGPT the text input. So we basically told ChatGPT, hey, you have 2 rooms, blah, 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 with those sensors, blah, blah, blah. Can you help us with basically those physical things, right? So, and this worked actually pretty well. So we got out a graph that actually looks quite well, represents mostly the ground truth situation, right? So we also did different tests. So we also, for example, tested out, does it help when we actually provide more information from PRIC? Because PRIC is a nice structured ontology, so, and we want to have a structured output. So does it actually help when we infuse that additional knowledge, that semantic knowledge from PRIC, in deriving a better graph? And the result was no, right? The graph is stronger simplified that we get out there. But interesting thing here, this graph is better at predicting. So, like I said, right, so simply a graph, stronger attention on spurious correlation, right, so you get out a better prediction model, right, so it does not mean, and that's, be careful, right, so better performance or prediction performance does not mean a more generalized model, right. And here you see actually the comparison for one of the extreme cases that we investigated, right? So, like I said, we turned off the HVAC system, room full of people is the situation. And you see the orange curve here in this case is the real behavior from the simulation, right? So, and you actually see the blue one, that's a ground truth. So that actually shows you also that actually our ground truth physically correct graph actually is performing best, right? Far from ideal, but performing best, because you always still or the model still overfits on the correlations, right? So, and you also then see then that the other GNNs that we generated with ChatGPT support here are performing a little bit worse, right? So none of them is really performing best, besides then the graph that I showed you with the PRIC connection, right? So then we scaled that up, right? So larger scenario, 20 rooms, similar setup, right? So, and we want to see, can we get ChatGPT to connect that graph? And the answer is no. Right? So then it gets simply too complex. So ChatGPT cannot scale to that complex scenario. Does just create very simple relationships between the HVAC system, the boilers, and the rooms are just clusters of temperature connections, right? So meaning it does not scale well to larger scenarios. Conclusion is, so GNNs do work better in predicting or building performance. So that's lesson learned number one. So yes, the physical constraints work better, still far from best, but better, right? Second is that yes, we can generate those graphs with ChatGPT support, right? So ChatGPT actually knows enough about building physics for that scenario, right? So, but at the moment they do not scale well. We're looking into that and improving the situation to get out technically bigger like then a working system. Yeah, thanks a lot.